Hello, and welcome to Science After Dark. If you enjoy calm, thought-provoking journeys through the universe, take a moment to like the video and subscribe to the channel. And before we begin, I'd love to know, where in the world are you listening from tonight? Somewhere under clear stars, or perhaps from a quiet room, far removed from the night sky. Either way, you're still part of this same vast universe we're about to explore. Now, settle in, because tonight we're not just looking up at the universe, we're gently drifting back to where it all began, not with a bang, not with a flash of light, but with something quieter, stranger, harder to imagine, a beginning that may not have been a moment at all. For most of human history, the night sky felt timeless, unchanging, eternal. The same stars, the same patterns, it was stretching endlessly into darkness. It was only in the last century that we began to realize something far more unsettling and far more beautiful. The universe has a history. It hasn't always looked the way it does now. Galaxies weren't always scattered across the cosmic web. Stars hadn't yet begun to shine. Even atoms, the building blocks of everything we know, did not yet exist. If we could somehow travel far enough into the distance, we wouldn't just be moving through space. We would be moving backward through time, past galaxies still forming, past the first stars flickering into existence, past a time when the universe was filled only with a soft, fading glow, and eventually we would arrive at a place where even light itself could not yet travel freely. A universe so hot, so dense, so unfamiliar that the laws of physics, as we understand them, begin to blur at the edges. And beyond that, we're not entirely sure. Some theories suggest a beginning, others suggest a transition, a phase change, or even a cycle in something far larger than our observable universe. Time itself may not behave the way we expect. It may not even exist in the way we experience it now. So tonight, we're not just asking how the universe began. We're asking something deeper. How does something come from almost nothing? How does structure emerge from simplicity? And how much of this story can we truly know? This is not a story of explosions and chaos. It's a story of cooling, of slowing, of tiny fluctuations growing almost imperceptibly into the vast cosmic structures we see today. A quiet unfolding. From the smallest particles to the largest galaxies to the place you're sitting right now. And as we move through this story together, from the earliest moments we can understand to the limits of what we can even imagine, take your time, there's no rush, because the universe itself took billions of years to become what it is, and tonight we'll follow that journey. One gentle step at a time. When we try to imagine the beginning of the universe, something unusual happens almost immediately, not out there in space, but inside our own thinking. Because the moment we ask what came before the universe, we're already assuming that the idea of before makes sense, and that is not guaranteed. In everyday life, time feels simple. One moment follows another, cause leads to effect. Morning becomes afternoon, and afternoon slowly settles into night. It feels natural to imagine that if something exists now, something must have come before it. But when physicists began to study the universe as a whole, they discovered that time itself may not be as solid or as universal as it seems. One of the more quietly radical ideas comes from a physicist named Julian Barber, who has spent much of his career exploring the possibility that time, as we experience it, might not be fundamental at all. Instead of a flowing river carrying events from past to future, Barber suggests that the universe may be better described as a vast collection of possible configurations, snapshots of reality, each complete in itself. In this view, what we perceive as the passage of time could emerge from the relationships between these configurations. Change creates the impression of motion. Memory creates the impression of a past, but underneath it all there may be no universal ticking clock. If that sounds slightly unsettling, you're not alone. Even among physicists this idea is still debated, but it points towards something important. The concept of before the universe might not just be unknown. It might not be a meaningful question at all. A similar idea appears in the work of Carlo Rovelli, a theoretical physicist known for his contributions to loop quantum gravity. Rovelli describes time not as a fixed background, but as something that emerges from interactions between physical systems. In his relational view of time, there is no single universal timeline that applies everywhere. Instead, time is local, dependent on relationships, and tied to the way systems influence one another. Without interactions, without change, without processes unfolding, time, in the way we experience it, may not exist. So when we imagine a moment before the universe began, we may be trying to place time in a context where it has not yet formed. It is a bit like asking what lies north of the North Pole. The question feels reasonable, until you realize the direction itself breaks down. Interestingly, this tension between beginnings and cycles is not new. Long before modern cosmology, many ancient traditions imagined the universe not as something with a single starting point, but as something that moves through cycles. In early Indian cosmology, for example, the universe was described as passing through vast repeating phases of creation and dissolution, sometimes called kalpas, each lasting billions of years in symbolic terms. Similarly, certain ancient Greek philosophers, such as the Stoics, imagined a universe that periodically resets itself in a great cosmic cycle known as ekpyrosis. These ideas were not based on observational astronomy in the modern sense, but they reflect a long-standing human intuition that perhaps the universe does not have a simple singular beginning. Modern physics does not confirm these ancient models in their original form, but it has, in some ways, circled back to similar possibilities. There are contemporary theories that explore cyclic universes, bouncing cosmologies, and even scenarios in which our observable universe is just one phase within a much larger system. The key difference is that today, these ideas are tested against data, equations, and observations, rather than purely philosophical reasoning. And that brings us to an important shift. Cosmology, as a science, is not primarily concerned with absolute origins in the philosophical sense. Instead, it focuses on transitions. It asks how the universe changed from one state to another, how it evolved from simplicity into complexity, how structure emerged over time. Rather than asking what came from nothing, cosmologists often ask what came from what we can measure. And what we can measure begins with evidence. In the early 20th century, astronomers began to notice something subtle but profound when they looked at distant galaxies. Light, when spread out into its spectrum, carries a kind of fingerprint. Specific elements absorb and emit light at precise wavelengths, creating patterns that can be recognized across vast distances. This technique, known as spectroscopy, allowed scientists to identify not just what distant objects were made of, but how they were moving. And what they found was quietly astonishing. The light from distant galaxies was shifted toward longer wavelengths, toward the red end of the spectrum. This phenomenon is called redshift. At first, it might seem like a small detail, a slight stretching of light. But when interpreted through the physics of waves, redshift reveals motion. It shows that the source of the light is moving away from the observer, and as more galaxies were observed, a pattern began to emerge. Nearly all of them were moving away, not in random directions, but in a consistent large-scale pattern. The farther away a galaxy was, the faster it appeared to be receding. This observation would eventually be formalized into what we now call Hubble's law, named after Edwin Hubble, though it builds on earlier work by Vesto Slipher and theoretical insights from Georges Lemaitre. Together, these discoveries suggested something remarkable. The universe was not static. It was expanding. Space itself was stretching, carrying galaxies along with it. And if the universe is expanding now, then in the past it must have been smaller, denser, hotter. Not infinitely long ago, but a finite time in the past, everything we can observe today may have been compressed into a much more compact state. This does not yet tell us what happened at the very beginning, or whether there even was a single beginning. But it does give us a direction, a way to trace the universe backward, step by step, using observation instead of assumption. And as we follow that path, something remarkable begins to unfold. Not a sudden explosion, but a gradual story, a quiet unfolding of structure, energy, and form, emerging from conditions that are still, even now, only partially understood. And so, rather than starting with a definitive beginning, we begin with something gentler, a shift, a realization that the universe is not fixed, it changes, it evolves, and by carefully observing those changes, we can begin to piece together its story. Once astronomers began to look more carefully at distant galaxies, something subtle started to appear in the light itself. Not something dramatic at first glance, not a sudden shift or a bright flash. No, just a quiet stretching, almost as if the light had been gently pulled apart during its journey across space. To understand what they were seeing, it helps to begin with the nature of light itself. Light travels as a wave, and each wave has a wavelength, the distance between its peaks. Different wavelengths correspond to different colours. Shorter wavelengths appear blue. Longer wavelengths appear red. When an object moves away from us, the waves it emits are stretched. The wavelength becomes longer, shifting toward the red end of the spectrum. This is known as redshift. It is closely related to something familiar in everyday life. When an ambulance passes by, the pitch of its siren changes. As it approaches, the sound waves are compressed, raising the pitch. As it moves away, the waves stretch, lowering the pitch. This is called the Doppler effect. Light behaves in a similar way. So when astronomers measure redshift in the light from a distant object, they are not just seeing colour, they are seeing motion. The first person to systematically measure this effect in galaxies was Vesto Slipher, working at the Lowell Observatory in Arizona in the early 1900s. Using spectroscopy, Slipher analysed the light from what were then called spiral nebulae. At the time, it was not yet clear whether these objects were part of our own galaxy or something much larger. What Slipher found was unexpected. Most of these objects showed significant redshift. They were moving away, and not slowly. Some were receding at speeds of hundreds of kilometers per second. far faster than typical stellar motions within the Milky Way. And this raised a quiet but profound question. If these objects were within our galaxy, why were they moving so rapidly away from us? Or perhaps they were not within our galaxy at all. This question would be addressed by Edwin Hubble, working at the Mount Wilson Observatory in California, using the 100-inch Hooker telescope, one of the most powerful instruments of its time. In the 1920s, Hubble studied these same spiral nebulae and identified a specific type of star within them known as Cepheid variables. Cepheid variables have a remarkable property. Their brightness varies in a regular cycle, and the period of that cycle is directly related to their intrinsic luminosity. This relationship was discovered by Henrietta Swan Leavitt at the Harvard College Observatory. By measuring the period of a Cepheid's brightness changes, astronomers can determine how bright it truly is, and by comparing that to how bright it appears from Earth, they can calculate its distance. Using this method, Hubble demonstrated that these spiral nebulae were not nearby objects. They were entire galaxies, far beyond the Milky Way. Suddenly, the scale of the universe expanded dramatically. What had once been thought of as a single galaxy became just one among many. And when Hubble combined these distance measurements with Slipher's redshift data, a pattern emerged that would reshape cosmology. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship is now known as Hubble's law, and it can be described in simple terms. Thus, the velocity of a galaxy moving away is equal to a constant multiplied by its distance. This constant is called the Hubble constant, and it sets the rate at which the universe is expanding. At first glance, this might sound as though we are at the center of everything, with galaxies flying away in all directions. But that is not what is happening. A helpful way to imagine this is to picture dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No single point is the center of the expansion on the surface itself. In the same way, space itself is expanding. Galaxies are not simply moving through space, they are being carried apart as space stretches. This idea was not entirely new. Around the same time, a Belgian physicist and priest named Georges Lemaître had been working independently on solutions to Albert Einstein's equations of general relativity. Einstein's equations describe how matter and energy influence the curvature of space-time. When Lemaître applied these equations to the universe as a whole, he found that a static universe was unstable. Instead, the mathematics naturally led to an expanding or contracting universe. In 1927, Lemaître published a paper proposing that the universe was expanding and that galaxies were receding from one another. He even derived a relationship between distance and velocity, similar to what would later be called Hubble's law. At the time, his work received little attention. It was published in a relatively obscure journal and written in French. But as observational evidence accumulated, Lemaître's theoretical insight became increasingly important. It provided a framework that connected observation with deeper physical laws. As the decades passed, astronomers continued refining measurements of cosmic distances and expansion rates. One of the key figures in this effort was Alan Sandage, a student of Edwin Hubble, who spent much of his career improving the accuracy of the Hubble constant. Measuring cosmic distances is not straightforward. It involves a chain of methods known as the cosmic distance ladder, where each step builds on the previous one. Cepheid variables are used to measure relatively nearby galaxies. For more distant objects, astronomers rely on other indicators, such as Type 1a supernovae, which have a consistent intrinsic brightness. By carefully calibrating these methods, Sandage and others work to reduce uncertainties and improve our understanding of the scale and age of the universe. Even today, this process is ongoing. There is currently a tension between different measurements of the Hubble constant known as the Hubble tension, where values derived from the early universe differ slightly from those measured in the local universe. This suggests that there may still be aspects of cosmology that are not fully understood. As these discoveries unfolded, alternative explanations were also proposed. One such idea was the tired light hypothesis, which suggested that light might gradually lose energy as it travels through space, leading to a red shift without requiring expansion. At first, this might seem like a simpler explanation, but when examined more closely, it failed to account for several key observations. For example, tired light does not explain the time dilation observed in distant supernovae, where events appear stretched in time in a way consistent with an expanding universe. It also struggles to match the detailed patterns seen in the cosmic microwave background. Over time, as more evidence accumulated, the expansion of space itself became the most consistent and comprehensive explanation. And with that realization came a deeper implication. If the universe is expanding now, then in the past everything must have been closer together. Galaxies that are billions of light years apart today would once have been much nearer to one another. The density of matter would have been higher. The temperature would have been greater. If we continue this reasoning backward, we arrive at a picture of a universe that was once extremely dense and extremely hot. Not as a single point in space, but as a state of the entire universe. This is one of the key ideas behind what is now called the Big Bang model. It does not describe an explosion in space, but rather an expansion of space from an earlier, denser state. And importantly, this conclusion does not come from speculation alone. It emerges from observation, from careful measurements of light, from the steady accumulation of data across decades of work by astronomers, physicists, and observatories around the world. It is a quiet discovery in many ways. No single moment where everything suddenly became clear. Just a gradual shift in understanding as pieces of evidence began to align. A realization that the universe is not static, not unchanging, not fixed in place. It is dynamic. It is evolving. And by observing that motion, by tracing the gentle stretching of light across vast distances, we begin to uncover a story that leads us further and further back, toward a time when everything we know was compressed into a state far different from anything we experience today. By this point, a quiet but powerful idea has taken shape. The universe is expanding. Not just that galaxies are drifting apart through space, but that space itself is stretching, carrying everything along with it. And if we follow that expansion backward in time, the distances between galaxies shrink, the density increases, the temperature rises. Eventually we arrive at a state where the universe was far hotter, far denser, and far more uniform than it is today. This is where the term Big Bang enters the story. Although the name might suggest something dramatic, even explosive, it can be slightly misleading. Because the Big Bang was not an explosion in space, it was an expansion of space. That distinction is subtle, but it changes everything. In an ordinary explosion, like a firework or a volcanic eruption, material is thrown outward into a pre-existing space. There is a center, a point from which everything spreads outward. But in the case of the universe, There is no center in that sense. Every region of space is expanding relative to every other region. There is no single point that we can identify as the origin of the expansion within the universe itself. A useful way to think about this is to imagine a loaf of bread rising in an oven, with raisins embedded throughout the dough. As the bread expands, each raisin moves away from the others. From the perspective of any single raisin, it looks as though all the others are receding. But there is no special raisin at the center of the expansion. The expansion is happening everywhere, all at once. In the same way, the Big Bang describes a state in which the entire universe was once much more compressed, and has been expanding ever since. The name itself has an interesting origin. It was coined, somewhat playfully, by the British astronomer Fred Hoyle during a radio broadcast in the late 1940s. Hoyle was not a supporter of the idea. In fact, he preferred a very different model of the universe, known as the steady-state theory. In the steady-state model, the universe has no beginning and no end. It expands over time, but new matter is continuously created to keep the overall density constant. This allowed the universe to appear roughly the same on large scales, regardless of when it was observed. Hoyle, along with collaborators Hermann Bondi and Thomas Gold, developed this model as an alternative to what they saw as the philosophical difficulty of a universe with a beginning. Later, the Indian astrophysicist Jayant Narlikar expanded on these ideas, working with Hoyle to develop more detailed versions of steady-state cosmology. For a time, the steady-state theory was taken seriously as a competing explanation. It had an appealing simplicity. No beginning, no special moment, no need to explain initial conditions. But as observational evidence improved, the balance began to shift. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided strong support for a hot, dense early universe. This faint glow, present in every direction, is exactly what the Big Bang model predicts as the leftover radiation from a time when the universe was much hotter and more opaque. The steady-state model struggled to account for this observation. Over time, as more data accumulated, including measurements of galaxy evolution and elemental abundances, the Big Bang framework became the dominant model in cosmology. Even Fred Hoyle, despite his continued skepticism about certain aspects, contributed significantly to our understanding of how elements are formed inside stars through processes known as stellar nucleosynthesis. So while the steady-state model did not ultimately prevail, it played an important role in sharpening the questions and strengthening the evidence. Science often advances in this way, through competing ideas that are gradually tested and refined, and the Big Bang model, as it stands today, is best understood not as a single event, but as a framework. It describes how the universe evolved from an early hot, dense state into the complex structure we observe now. It explains why distant galaxies are moving away. It accounts for the cosmic microwave background. It predicts the relative abundances of light elements such as hydrogen and helium. In many ways, it is one of the most successful scientific models we have, but it is not a complete explanation of everything. Thus, one of the key challenges is known as the initial conditions problem. The Big Bang model tells us how the universe evolved from its early state, but it does not fully explain why that state had the specific properties it did. Why was the universe so uniform on large scales? Why were there small fluctuations in density, just enough to allow galaxies to form? Why did the laws of physics take the particular form that they do? These are questions that reach beyond the standard Big Bang framework. They point toward deeper layers of physics that are still being explored. Another important limitation is that as we trace the universe back to earlier and earlier times, our current theories begin to break down. General relativity, which describes gravity and the large-scale structure of space-time, works extremely well under many conditions. Quantum mechanics, which governs the behavior of particles on the smallest scales, is also highly successful. But when we try to apply both theories together at extremely high energies and densities, such as those present in the earliest moments of the universe, they become difficult to reconcile. This is why physicists continue to search for a theory of quantum gravity, a framework that can unify these two pillars of modern physics. Until such a theory is fully developed and tested, there will remain limits to how far back we can confidently describe the universe. It is also worth noting that the Big Bang model does not necessarily describe the absolute beginning of everything. It describes the earliest phase that we can currently model with confidence, and there may have been processes or states that preceded it, or transitions that led into it. Some theories suggest that what we call the Big Bang could be the result of a prior phase, such as a contraction followed by a bounce, or a transition from a different kind of vacuum state. Others explore the possibility that our universe is one region within a much larger multiverse. These ideas remain speculative, but they highlight an important point. The Big Bang is not the final word. It is a powerful and well-supported description of cosmic history, but it is also part of a larger, evolving effort to understand the universe at its deepest levels. And as we continue to refine our observations and develop new theories, the picture may become even more detailed. For now, what we can say with confidence is this. The universe was once much hotter and much denser than it is today. It has been expanding for billions of years, and the traces of that early state are still visible, encoded in the light and structure we observe across the cosmos. From this foundation, we can begin to explore the earliest moments that our current physics can describe. Moments when the universe was not filled with stars or galaxies, but with energy, particles, and rapidly changing conditions. A time when the familiar world had not yet taken shape, and where the story of everything we see around us was just beginning to unfold. As we continue to trace the universe backward toward earlier and earlier moments, something unexpected begins to emerge. The universe, on the largest scales we can observe, appears remarkably smooth. If you look out across billions of light years, galaxies are distributed in a way that is broadly uniform. Not perfectly so, but close enough that, on average, the universe looks the same in every direction. This property is known as large-scale homogeneity. There is also isotropy, meaning the universe appears similar no matter which direction we look. Together, these observations form what is called the cosmological principle. At first, this might seem entirely reasonable, but when physicists began to examine the implications more closely, they realized something puzzling. If the universe has been expanding over time, and if signals such as light can only travel at a finite speed, then distant regions of the universe should not have had enough time to influence each other. In other words, parts of the universe that are now extremely far apart should never have been in causal contact. They should not have had any way to exchange information, energy, or heat, and yet they appear to have nearly identical properties. This is known as the horizon problem. There is also another subtle issue called the flatness problem. Measurements indicate that the geometry of the universe is very close to flat, meaning that the overall curvature of space-time is nearly zero. But in general relativity, a perfectly flat universe is an unstable condition. Even small deviations from flatness would grow over time, leading to a universe that is either strongly curved inward or outward. The fact that the universe appears so close to flat today suggests that it must have been extraordinarily fine-tuned in its earliest moments. These problems are not contradictions, but they do suggest that something important is missing from the simplest version of the Big Bang model. This is where the idea of cosmic inflation enters the story. In the early 1980s, a physicist named Alan Guth proposed a bold solution. He suggested that, in the very earliest fraction of a second after the universe entered its hot, dense phase, it underwent a period of extremely rapid expansion. Not just expansion in the usual sense, but an exponential expansion, where the size of the universe increased by an enormous factor in an incredibly short time. To give a sense of scale, during inflation, a region of space smaller than an atom could have expanded to a size larger than a galaxy in a tiny fraction of a second. Then this process would have smoothed out any initial irregularities, much like stretching a wrinkled piece of fabric until it appears flat and uniform. It would also explain why distant regions of the universe appear so similar. Before inflation, those regions could have been close enough to interact and reach a common temperature. Then, inflation would have rapidly pushed them far apart, preserving that uniformity across vast distances. At around the same time, the Russian physicist Alexei Starobinsky developed an independent model of inflation based on modifications to general relativity. His approach showed that inflation could arise naturally from the behavior of spacetime itself under certain conditions. These early models laid the foundation for what would become one of the most influential ideas in modern cosmology. But as with many powerful ideas, inflation did not remain simple for long. In the years that followed, Andrei Linde extended the concept into something even more expansive. He proposed the idea of eternal inflation. In this picture, inflation is not a single event that happened once and then stopped everywhere. Instead, it continues in different regions of space. Some regions stop inflating and form universes like ours, while others continue expanding. This leads to a picture in which our observable universe is just one bubble within a much larger multiverse. Each bubble could, in principle, have different physical properties, depending on how inflation ended in that region. Different values for physical constants, different types of particles, perhaps even different laws of physics. It is a vast and somewhat dizzying idea, but it arises naturally from certain models of inflation, and it raises new questions. If there are infinitely many such regions, how do we define probabilities? How do we say what is typical, or likely, in an infinite multiverse? This is known as the measure problem. In everyday situations, probability is relatively straightforward. If you flip a coin, there are two outcomes, and each has a clear likelihood. But in an infinite system, where every possible outcome may occur infinitely many times, defining probability becomes much more subtle. Different ways of counting or comparing regions can lead to different answers, and without a clear measure, it becomes difficult to make precise predictions. This is one of the ongoing challenges in inflationary cosmology. At the same time, not all physicists are entirely satisfied with inflation as an explanation. One of the most thoughtful critiques comes from Roger Penrose, a mathematical physicist known for his work on black holes and the structure of space-time. Penrose has pointed out that inflation, while it explains the large-scale smoothness of the universe, may not fully address the deeper question of initial conditions. In particular, he focuses on the concept of entropy. Entropy is a measure of disorder, or the number of possible microscopic configurations corresponding to a given macroscopic state. In thermodynamics, systems tend to evolve toward higher entropy over time. The early universe, however, appears to have had extremely low entropy. This is somewhat surprising because high density and high temperature are often associated with high entropy. But when gravity is taken into account, the situation changes. A smooth, uniform distribution of matter actually represents a very special, low-entropy state in a gravitational system. Clumped matter, such as galaxies and black holes, corresponds to higher entropy. So the early universe, being so smooth, was in a highly ordered state. Penrose has argued that the probability of such a low-entropy initial condition is extraordinarily small. He has even estimated that the odds are something like 1 part in 10 raised to the power of 10 raised to the power of 123, an unimaginably tiny number. His point is not necessarily that inflation is wrong, but that it may not fully explain why the universe began in such a special state. It may shift the question rather than resolve it. This brings us back to a broader perspective. Inflation is a powerful and elegant idea. It explains several key features of the universe, including its large-scale uniformity and the origin of small fluctuations that later grew into galaxies. It is supported by observations of the cosmic microwave background, which show patterns consistent with inflationary predictions. At the same time, it opens the door to deeper questions about probability, initial conditions, and the nature of reality itself. It is both explanatory and incomplete, a step forward, but not the final answer. And perhaps that is part of the beauty of it. Each layer of understanding reveals another layer beneath it. Each solution brings with it new questions. As we continue moving backward toward the earliest moments we can meaningfully describe, the universe becomes less familiar. Energy dominates over matter. Forces behave differently, and the conditions become so extreme that even our best theories begin to stretch. But within that unfamiliar territory lies the origin of everything that would come later. Not in the form of stars or galaxies, but in the form of tiny fluctuations, seeds of structure, emerging from processes that are still, even now, being carefully explored. As we move deeper into the earliest phases of the universe, something quite surprising begins to take shape. The laws of physics, which today seem fixed and distinct, may not always have been so clearly separated. In the earliest moments, the universe was not only hot and dense, but also remarkably simple in a very specific way. It may have been governed by symmetries that no longer exist in the same form today. In physics, symmetry does not simply mean visual balance or aesthetic appeal. It refers to something more precise. A symmetry is a property of a system that remains unchanged under certain transformations. For example, if the laws of physics are the same regardless of where you are in space, that is a type of symmetry known as translational symmetry. If they remain the same over time, that is temporal symmetry. And if certain physical processes behave identically under different internal transformations, those are called gauge symmetries. These symmetries are not just mathematical curiosities, they are deeply connected to the fundamental forces of nature. One of the most important ideas in modern physics is that forces arise from symmetries. This connection was formalized through Noether's theorem, developed by the mathematician Emmy Noether in the early 20th century. Her work showed that for every continuous symmetry in a physical system, there is a corresponding conserved quantity. For example, symmetry in time leads to conservation of energy. Symmetry in space leads to conservation of momentum. These are not coincidences, they are reflections of underlying structure. Now, in the very early universe, it is believed that these symmetries were even more unified. The forces we now distinguish as separate may have once been part of a single combined interaction. Today, we recognize 4 fundamental forces: gravity, described by general relativity; electromagnetism, governing electric and magnetic interactions; the strong nuclear force, SGE, which binds protons and neutrons within atomic nuclei; and the weak nuclear force, responsible for certain types of radioactive decay. At the energy scales we experience in everyday life, these forces behave quite differently. But as we move to higher energies, closer to those present in the early universe, some of these distinctions begin to blur. In the 1960s, physicists Sheldon Glashow, Abdus Salem, and Steven Weinberg developed what is now known as the electroweak theory. This theory showed that electromagnetism and the weak nuclear force are actually different aspects of a single, unified interaction at high energies. As the universe cooled, this symmetry was broken, and the 2 forces became distinct, and Steven Weinberg's contributions were particularly important in demonstrating how this unification could be described mathematically and connected to observable phenomena. This idea of symmetry breaking is central to our understanding of the early universe. To get a sense of how it works, it helps to think in terms of phase transitions. A familiar example is water. At high temperatures, water exists as a gas, with molecules moving freely and randomly. As it cools, it condenses into a liquid and then freezes into a solid. Each of these phases has different properties, even though the underlying substance is the same. The transitions between these phases are known as phase transitions. In the early universe, similar transitions occurred, but on a much more fundamental level. As the universe expanded and cooled, these symmetries that once unified the forces began to break. Each transition gave rise to new distinctions, new behaviors, and new structures. The electroweak symmetry breaking, for example, is associated with the Higgs field, a pervasive field that gives mass to certain particles. The existence of the Higgs field was confirmed experimentally at the Large Hadron Collider at CERN in 2012 through the detection of the Higgs boson. This discovery provided strong support for the Standard Model of particle physics, which describes the known fundamental particles and their interactions, excluding gravity. But even the Standard Model is not the final story. It is highly successful in explaining a wide range of phenomena, yet it leaves several important questions unanswered. For instance, it does not fully account for gravity at the quantum level. It does not explain the nature of dark matter, which appears to make up a significant portion of the universe's mass. And it does not address why the fundamental constants of nature have the values that they do. Because of these limitations, physicists have proposed various extensions beyond the Standard Model. One such idea is grand unified theories, often referred to as just WUTs. These theories attempt to unify the strong nuclear force with the electroweak interaction into a single framework at extremely high energies. At even higher energies, some models suggest that all forces, including gravity, might be unified in a theory of everything. String theory is one of the more well-known approaches in this direction. It proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings, whose different modes of vibration correspond to different particles. Loop quantum gravity is another approach, focusing on quantizing spacetime itself rather than introducing new fundamental objects. These ideas remain under active investigation, and as of now, there is no experimental confirmation that clearly favours one over the others. But they offer a glimpse into how the early universe may have operated under conditions far beyond anything we can recreate directly. What is particularly striking is how these microscopic processes connect to the large-scale structure of the universe. The symmetries and their breaking determine the behaviour of particles, the strengths of forces, and the ways in which matter could interact. These, in turn, influenced how matter clumped together, how energy flowed, and how structures began to form. Even small differences in these early conditions could have led to a universe that looks very different from the one we observe today. A slight change in the strength of the strong nuclear force, for example, could prevent protons and neutrons from binding together. Without that binding, atomic nuclei would not form. Without atomic nuclei, there would be no atoms, and without atoms, there would be no stars, no chemistry, and no familiar matter at all. In this sense, the early universe can be seen as a kind of blueprint, not a fixed design, but a set of conditions and rules that shaped everything that followed. The cooling of the universe was not just a loss of energy, it was a process of differentiation. From a unified symmetrical state, the universe gradually developed complexity. Forces separated, particles acquired mass, interactions became more varied, and from this evolving framework the building blocks of matter began to take shape. What started as a nearly uniform field of energy began to organize itself, step by step, into something capable of forming structure. And while much of this story is grounded in well-tested theory and observation, there are still many open questions. We do not yet know exactly how all the forces might unify at the highest energies. We do not know whether the constants of nature are truly constant, or if they could vary under different conditions. And we do not yet have a complete theory that combines quantum mechanics and gravity into a single consistent framework. But even with these uncertainties, one thing becomes clear. The laws of physics, as we experience them today, are not simply given. They are the result of a history that began in a state of great asymmetry and evolved through a series of transitions into the rich and varied universe we now observe. And as we continue to follow that history, we move closer to understanding how the first particles formed, how matter emerged from energy, and how the foundations of everything we see were quietly established in those earliest moments. If we continue gently tracing the universe backward, toward its earliest conditions, we arrive at a moment where something very delicate and very important took place. A moment that quietly determined whether anything like stars, planets, or even atoms would ever exist at all. Because in those early stages, the universe did not clearly prefer matter over antimatter, and that is where the mystery begins. According to our best understanding of high-energy physics, whenever energy is converted into particles, it tends to produce matter and antimatter in equal amounts. For every particle, there is a corresponding antiparticle. Electrons have positrons. Protons have antiprotons. These pairs are nearly identical, except for opposite electric charge and certain quantum properties. When a particle meets its antiparticle, they annihilate each other, converting their mass back into energy. typically in the form of high-energy photons. This process is extremely efficient. So if the early universe had produced exactly equal amounts of matter and antimatter, then as the universe cooled, these pairs would have found each other and annihilated almost completely. What would remain is a universe filled mostly with radiation, with very little matter left behind, no atoms, no stars, no galaxies, and certainly no observers quietly reflecting on cosmic history. But that is not what we see. Instead, the observable universe is overwhelmingly composed of matter. Antimatter exists, but only in trace amounts, typically produced in high-energy processes such as cosmic rays or particle collisions in accelerators like the Large Hadron Collider at CERN. So something must have introduced a small imbalance, a slight preference for matter over antimatter, a difference so tiny that it might almost seem insignificant. And yet, it made all the difference. This process is known as baryogenesis. The term comes from baryon, referring to particles like protons and neutrons, which make up most of the visible matter in the universe. Baryogenesis describes the mechanisms by which this asymmetry between matter and antimatter may have arisen. To understand what is required for such an imbalance to develop, we turn to the work of Andrei Sakharov, a Soviet physicist who, in 1967, outlined 3 necessary conditions. These are now known as the Sakharov conditions. First, there must be processes that violate baryon number conservation. In simpler terms, the laws of physics must allow for situations where the total number of baryons is not strictly conserved. Second, there must be a violation of what is called charge and parity symmetry, here often abbreviated as CP symmetry. Charge symmetry refers to replacing particles with their antiparticles. Parity symmetry involves flipping spatial coordinates, like looking at a mirror image. If CP symmetry were perfectly conserved, matter and antimatter would behave in exactly the same way, making it impossible for an imbalance to develop. Third, these processes must occur out of thermal equilibrium. In a system that is perfectly balanced and stable, any asymmetry that begins to form would be quickly erased. But in a rapidly changing environment such as the early universe, departures from equilibrium can allow small differences to persist and grow. These 3 conditions together provide a framework. They do not specify exactly how baryogenesis occurred, but they outline what must be true for it to happen. Over the years, physicists have searched for evidence of these conditions in both theory and experiment. One of the key areas of investigation has been CP violation. In the 1960s, experiments involving particles called neutral kaons revealed that CP symmetry is not perfectly conserved in nature. Later, similar effects were observed in systems involving B mesons, studied at facilities such as the Bell experiment in Japan and the Babar experiment in the United States. These discoveries confirmed that CP violation exists. However, the amount observed within the standard model of particle physics appears to be too small to account for the matter-antimatter imbalance we see in the universe. This suggests that there may be additional sources of CP violation that have not yet been detected, perhaps in processes involving neutrinos, or in physics beyond the standard model. There are several proposed mechanisms for baryogenesis. One idea is electroweak baryogenesis, which suggests that the asymmetry arose during the electroweak phase transition, when the electromagnetic and weak forces separated. Another is leptogenesis, which involves an asymmetry in leptons, such as neutrinos, that is later converted into a baryon asymmetry. These ideas are still under active investigation, and no single explanation has been definitively confirmed. But what is clear is that the imbalance between matter and antimatter is extremely small. Estimates suggest that for every billion pairs of matter and antimatter particles, there was only one extra matter particle. That is a difference of 1 part in a billion. And yet, after all the annihilations took place, that tiny surplus is what remained. Everything we see today, every atom, every star, every galaxy, is built from that small excess. It is a reminder that even the smallest differences can have enormous consequences when given enough time and space to unfold. There is something quietly remarkable about that. The entire visible universe, in all its complexity, emerging from a slight imbalance in the earliest moments. Not a dramatic shift, but a subtle tilt. A preference so slight it could easily be overlooked, and yet it shaped everything that followed. As the universe continued to expand and cool, the conditions changed once again. The energy densities dropped, the interactions between particles became less frequent, and instead of constant creation and annihilation, particles began to persist. Quarks, the fundamental building blocks of protons and neutrons, began to combine in stable ways. Gluons, which mediate the strong nuclear force, bound these quarks together into composite particles. This process is governed by quantum chromodynamics, the theory describing the strong interaction. At extremely high energies, quarks move freely in a state known as quark-gluon plasma. But as the universe cooled below a certain temperature, roughly 2 trillion degrees Kelvin, quarks became confined within hadrons, such as protons and neutrons. This transition is sometimes called quark confinement. It marks a significant step in the emergence of matter as we recognize it. From a nearly uniform sea of energy and fundamental particles, the universe began assembling more complex structures, stable building blocks, units that could persist, although interact, and eventually combine into larger systems. And all of this rests on that earlier asymmetry. Without it, the particles forming now would have been annihilated long ago. The universe would have remained a bath of radiation, smooth and empty of structure. Instead, because of that slight imbalance, matter survived, and with it, the possibility of everything that would come later. As we continue forward, the focus shifts from why matter exists at all to how it begins to organize itself, from individual particles to the first nuclei, from the smallest scales to the beginnings of structure. A quiet progression built on foundations that were set in place almost as soon as the universe began to evolve. As the universe continued to expand and cool, something subtle but deeply important began to happen. The fundamental particles that once moved freely through an intensely energetic environment started to settle into more stable arrangements. This was not a sudden transformation, but a gradual shift in behavior as the conditions of the universe changed. At extremely high energies, in the earliest moments, quarks and gluons existed in a state known as quark-gluon plasma. In this state, quarks were not bound into larger particles. They moved independently, interacting through the strong nuclear force carried by gluons. It is a strange and unfamiliar phase of matter, one that has been recreated briefly in experiments at facilities like the Large Hadron Collider at CERN and the Relativistic Heavy Ion Collider in the United States. In these experiments, heavy ions are accelerated to nearly the speed of light, and then collided. You are producing temperatures of trillions of degrees. For a fleeting moment, conditions similar to those of the early universe are recreated, allowing physicists to study how quarks behave when they are not confined. What these experiments reveal is that quarks, under such conditions, behave almost like a fluid, moving collectively rather than as isolated particles. But this state cannot last forever. As the universe expanded, the average energy decreased, temperatures fell, and as they did, the behavior of quarks began to change. This transition is governed by a theory known as quantum chromodynamics, often abbreviated as QCD. Quantum chromodynamics describes how quarks interact through the strong force, mediated by gluons. It is one of the central components of the standard model of particle physics. In the 1970s, the physicists David Gross and Frank Wilczek, along with David Politzer, made a key discovery within this framework. They found that the strength of the strong force depends on distance. At very short distances, or equivalently at very high energies, quarks interact weakly with one another. This property is known as asymptotic freedom, but as quarks move farther apart, the force between them becomes stronger. This is the opposite of what we experience with gravity or electromagnetism, where forces weaken with distance. In quantum chromodynamics, trying to pull quarks apart actually increases the energy of the system. Eventually, it becomes energetically favorable to create new quark-antiquark pairs, rather than allow a single quark to exist in isolation. This leads to a phenomenon known as confinement. Quarks are never found alone in nature. They're always bound together in composite particles called hadrons. As the universe cooled below a critical temperature, roughly 2 trillion degrees Kelvin, quark confinement took hold across the entire cosmos. Quarks combine to form stable structures. The most familiar of these are protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron is made of 2 down quarks and 1 up quark. These quarks are held together by gluons, constantly exchanging energy and momentum in a dynamic, ever-shifting internal structure. It is worth pausing for a moment to appreciate just how energetic this process is. Even though protons and neutrons are tiny, their internal energy is immense. In fact, most of the mass of a proton does not come from the mass of the quarks themselves, but from the energy of their interactions. As described by Einstein's mass-energy equivalence, energy is equal to mass multiplied by the speed of light squared. The energy contained within the strong force interactions contributes directly to the mass we observe. So when we think about matter forming in the early universe, we are really thinking about energy reorganizing itself into stable configurations, energy becoming structure, energy becoming mass. Once protons and neutrons formed, the universe had its first stable building blocks of matter. But the story does not end there. These particles existed in a hot, dense environment, constantly colliding and interacting with one another. At this stage, there were still no atoms, no nuclei, and just a dense mixture of protons, neutrons, electrons, photons, and other particles. The balance between protons and neutrons was determined by ongoing interactions mediated by the weak nuclear force. Neutrons are slightly heavier than protons, and over time, as the universe cooled further, some neutrons began to decay into protons, electrons, and neutrinos. This subtle difference in mass played an important role in determining the eventual composition of the universe. If the neutron had been just a little lighter or a little heavier, the balance between protons and neutrons would have shifted, leading to a very different outcome in later stages. This brings us to an intriguing idea. The fundamental constants of nature, such as particle masses and interaction strengths, appear to have very specific values. These values determine how particles behave, how forces act, and how structures form. But it's not entirely clear why these constants have the values that they do. Some theories suggest that they are fixed and fundamental, the same everywhere and at all times. Others explore the possibility that these constants could vary under different conditions or across different regions of a larger multiverse. In certain models of string theory, for example, there are many possible configurations of physical laws, each corresponding to a different set of constants. Our universe would then be one realization among many. These ideas remain speculative, but they highlight how sensitive the universe is to its underlying parameters. Even small changes in these constants could dramatically alter the outcome. A slight increase in the strength of the strong nuclear force could cause protons and neutrons to bind too easily, forming heavy nuclei too quickly. A slight decrease could prevent them from binding at all. In either case, the formation of stable elements, and eventually stars and planets, would be disrupted. So as protons and neutrons formed and began to interact, the stage was being set for the next major transition, the formation of atomic nuclei. This process, known as nuclear synthesis, would take place as the universe continued to cool, allowing protons and neutrons to combine into the first elements. But timing is everything. If the universe cooled too quickly, there would not be enough time for these reactions to occur. If it cooled too slowly, different reactions would dominate. In reality, the conditions were just right for the formation of the light nuclei such as hydrogen and helium, along with small amounts of lithium. This next step represents another quiet shift. From individual particles to the first simple structures, from isolated building blocks to the beginnings of chemistry. And it all traces back to these early moments, when quarks became confined, when protons and neutrons formed, and when the fundamental architecture of matter began to take shape. A process guided by the laws of physics, shaped by the conditions of the universe, and balanced on parameters that even now continue to invite careful reflection. As the universe continued its steady expansion, its temperature began to fall to a level where something new became possible. Protons and neutrons, which had formed earlier, were no longer constantly broken apart by high-energy collisions. For the first time, they could begin to come together and remain together. This marked the beginning of a process known as Big Bang nucleosynthesis. The term nucleosynthesis simply means the creation of atomic nuclei. It is the stage when the first elements in the universe were formed, not inside stars, but directly from the conditions of the early cosmos itself. This process took place within the first few minutes after the universe entered its hot, dense phase. Not hours, not days, but minutes. It is a remarkably brief window of time, yet it set the chemical foundation for everything that followed. To understand how this worked, it helps to picture the universe at that moment as a hot, dense mixture of protons, neutrons, electrons, photons, and neutrinos. The particles were still interacting frequently, but not so violently that all structure was immediately destroyed. One of the key factors at this stage was the ratio of neutrons to protons. Earlier, this ratio had been shaped by interactions involving the weak nuclear force. As the universe cooled, these interactions slowed down, and the ratio effectively became fixed at roughly 1 neutron for every 6 protons. This balance would determine which elements could form. The simplest possible nucleus is hydrogen, consisting of a single proton. But hydrogen is not the only possibility. If a proton and a neutron come together, they can form deuterium, a heavier form of hydrogen with 1 proton and 1 neutron. From there, additional combinations can lead to helium, which contains 2 protons and 2 neutrons. These reactions depend on temperature and density. If the universe is too hot, nuclei are immediately broken apart by energetic photons. If it is too cool, particles do not collide often enough to form nuclei efficiently. There is a narrow range of conditions where nucleosynthesis can proceed, and for a short period the universe passed through exactly that range. This process was first described in detail by Ralph Alpher and George Gamow in the late 1940s, along with their contributions from Robert Herman. They developed theoretical models predicting how the early universe would produce light elements. At the time, this was a bold idea. It suggested that the chemical composition of the universe could be traced back to its earliest moments. Over the decades, these predictions have been refined and tested. Modern work, including that of physicists like Keith Olive, has improved the precision of nucleosynthesis calculations, taking into account detailed nuclear reaction rates and updated measurements of cosmological parameters. The results are striking. The observed abundances of light elements in the universe closely match the predictions of Big Bang nucleosynthesis. About 75% of the ordinary matter in the universe is hydrogen. Roughly 25% is helium. There are also tiny amounts of deuterium and lithium. Heavier elements such as carbon, oxygen, and iron are not produced in significant quantities during this early phase. They would come much later, inside stars. This agreement between theory and observation is one of the strongest pieces of evidence supporting the Big Bang framework. It shows that the early universe behaved in a way that is consistent with our understanding of nuclear physics. But it also reveals something deeper. The outcome of nucleosynthesis is highly sensitive to the underlying conditions. Small changes in temperature, density, or the properties of particles could lead to very different results. For example, if the neutron-to-proton ratio had been slightly different, the amount of helium produced would change significantly. If nuclear reaction rates were even slightly altered, the balance between hydrogen and helium could shift. If the strength of the strong nuclear force were different, protons and neutrons might bind too easily, or not at all. In one scenario, nearly all hydrogen could be converted into helium, leaving little fuel for long-lived stars. In another, helium might not form efficiently, altering the entire pathway of stellar evolution. This sensitivity leads to a broader question. Why do the constants of nature have the values that they do? Why is the universe set up in a way that allows for the formation of stable nuclei, long-lived stars, and complex chemistry? This question is often referred to as the problem of fine-tuning. It does not necessarily imply design or intention, but it highlights the fact that the universe appears to operate within a narrow range of conditions that permit structure to emerge. If we imagine adjusting certain parameters, even slightly, the outcome can change dramatically. It is a bit like tuning a radio. A small shift in frequency can move you from a clear signal to static. In the same way, small shifts in physical constants could move the universe from one that supports complexity to one that does not. There are different ways to think about this. Some physicists view fine-tuning as a clue that deeper physical principles are at work, principles that determine these constants in a necessary way. Others consider the possibility that many different sets of constants exist across a larger multiverse, and we observe this particular set because it allows for observers like us to exist. This idea is sometimes associated with the anthropic principle. At present, there is no definitive answer. but the question itself remains an important part of modern cosmology. Returning to nucleosynthesis, once this brief window of element formation closed, the universe continued to expand and cool. Temperatures dropped below the level needed for nuclear reactions to proceed efficiently. The composition of the universe became largely fixed, at least in terms of light elements. What remained was a hot, ionized plasma, a mixture of nuclei and free electrons, along with a vast number of photons. In this state, light could not travel freely. Photons were constantly scattered by charged particles, particularly electrons, in a process known as Thomson scattering. The universe was effectively opaque, not in the sense of darkness, but in the sense that light could not move in straight, uninterrupted paths. It was more like a dense fog filled with glowing particles. As expansion continued, the temperature eventually fell low enough for another transition to occur. Electrons began to combine with nuclei to form neutral atoms. This process is known as recombination. When electrons became bound to nuclei, the number of free charge particles decreased, and photons were no longer scattered as frequently. The universe began to become transparent. Light, which had been trapped in constant interaction, was finally able to travel freely across space. This transition would leave behind a faint glow, a relic of the early universe, which we can still observe today. But before reaching that moment, there is something quietly remarkable to reflect on. Within just a few minutes, the universe had established its basic chemical composition. Hydrogen and helium, in proportions that would shape the formation of stars and galaxies for billions of years. A simple mixture, yet one that contains the potential for extraordinary complexity. All of it emerging from conditions that were balanced with remarkable precision. Not perfectly understood, not fully explained, but clearly constrained in a way that allowed structure to grow. And as the universe continued its slow cooling, it moved one step closer to becoming transparent, one step closer to revealing its history through the light that would soon begin its long journey across space. As the universe continued its slow and steady expansion, something gentle but transformative began to unfold. The temperature, once unimaginably high, had now fallen to a few thousand degrees Kelvin, still far hotter than anything we experience on Earth, but cool enough for a new kind of stability to emerge. Up to this point, the universe had been filled with the dense plasma, a mixture of positively charged nuclei and negatively charged electrons, along with an immense sea of photons. In this state, light could not travel freely. Photons were constantly interacting with charged particles, especially electrons, in a process known as Thomson scattering. Every time a photon attempted to move, it would almost immediately be deflected. Its path would zigzag unpredictably, like a beam of light trying to pass through a thick fog. This meant that the universe, although filled with light, was effectively opaque, not dark, but hidden. There was no clear line of sight across large distances, no way for information carried by light to travel uninterrupted. But as the temperature dropped further, a threshold was reached. At around 3000 Kelvin, conditions allowed electrons to combine with protons and helium nuclei to form neutral atoms. This process is known as recombination. The name can be slightly misleading since it suggests something coming together again, but in this context, it refers to the first, stable formation of neutral atoms in the universe. Before this moment, electrons and nuclei could not remain bound. The energy of the surrounding photons was simply too high. any attempt at forming an atom would be quickly undone. But now, as the universe cooled, these combinations could persist. Hydrogen atoms formed, consisting of a single proton and a single electron. Helium atoms formed as well, with 2 protons, 2 neutrons and 2 electrons. And with the formation of neutral atoms, something profound happened. The number of free charged particles dropped dramatically. Without free electrons to scatter them, photons were suddenly able to travel much longer distances without interruption. They decoupled from matter. This transition is known as photon decoupling. Light, which had been trapped in constant interaction, was finally released. The universe became transparent. For the first time, photons could move in straight paths across vast stretches of space. If you could have been there, in some hypothetical sense, this would be the moment when the universe would begin to look clear. Not filled with stars or galaxies, those would come much later, but no longer obscured by a dense glowing fog. It is tempting to think of this as the universe turning on the lights, but in reality the light was already there. What changed was its freedom to travel, and this freedom carried with it something extraordinary: information. The photons released during this transition did not simply vanish. They have been travelling ever since, stretching along with the expansion of space. Their wavelengths have grown longer, their energy has decreased, but they still carry a record of the conditions at the moment they were set free. This makes recombination a kind of cosmic snapshot, a frozen image of the universe at a very early stage in its history. Not an image in the usual sense, but a pattern of radiation that encodes temperature variations, density fluctuations, and the distribution of matter at that time. These variations are extremely small, differences of about 1 part in 100,000, and yet they are crucial, because they represent the seeds from which all later structure would grow. Regions that were slightly denser would eventually attract more matter through gravity. Over time, these small fluctuations would develop into galaxies, clusters, and the vast cosmic web. But even at this early stage, the picture is not perfectly smooth. And understanding why requires looking at the behavior of matter and radiation just before recombination. This is where the work of Joseph Silk becomes important. Silk studied how small-scale fluctuations in the early universe would be affected by interactions between photons and matter. He showed that as photons scattered off electrons, they could diffuse from regions of higher density to lower density. This process, now known as silk damping, effectively smoothed out fluctuations on very small scales. It acted like a kind of gentle averaging process. Sharp variations were softened. Only fluctuations above a certain scale could survive. This has important consequences. It means that the structure we observe in the universe today is not simply a direct reflection of all initial variations. It has been filtered, smoothed on small scales, preserved on larger ones. And this filtering process is encoded in the pattern of radiation released during recombination. By studying these patterns, scientists can infer the conditions of the early universe with remarkable precision. In this sense, the universe has left behind a record of its own past, a kind of fossil radiation, still present everywhere, waiting to be observed. And this is what makes this moment so significant. It marks the boundary between what we can observe directly and what lies beyond our current reach. Before recombination, the universe was opaque. Light could not travel freely, and so we cannot see directly into that earlier era using electromagnetic radiation. After recombination, the universe became transparent. Light could travel, carrying information across billions of years. Everything we observe with telescopes, from nearby stars to distant galaxies, relies on this transparency. It is the reason the universe is visible at all, and the light released at this moment has not disappeared. It fills the entire universe, now cooled and stretched to much longer wavelengths. What was once visible, light has shifted into the microwave region of the electromagnetic spectrum. This radiation is faint, but measurable. It arrives from all directions, almost perfectly uniform with those tiny variations imprinted upon it. It is known as the cosmic microwave background. But before we explore that in detail, it is worth pausing here for a moment to consider what has just taken place. The universe has transitioned from a state where light was constantly interacting, unable to travel freely, to a state where light could move across vast distances. A shift from opacity to transparency, from confinement to freedom. And in that transition, it has preserved a record, a quiet imprint of its early conditions, a whisper from a time when the universe was only a few 100,000 years old, still simple, still smooth, but already carrying within it the subtle variations that would one day grow into everything we see around us. The light released during that quiet moment of recombination did not fade away or disappear. It has been travelling ever since, stretching, cooling, and spreading out as the universe expanded, but still present, everywhere. For a long time, this idea remained theoretical. Physicists like George Gamow, along with Ralph Alpher and Robert Herman, had predicted that if the universe began in a hot, dense state, there should still be a faint background glow filling all of space, a leftover radiation, cooled over billions of years, now residing in the microwave region of the electromagnetic spectrum. But for years, no one had detected it, not because it was not there, but because no one was quite looking for it in the right way. Then, in the mid-1960s, something unexpected happened. And at Bell Telephone Laboratories in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna designed for satellite communication experiments. They were trying to measure faint radio signals, but kept encountering a persistent background noise. It was uniform, it came from all directions, and it did not vary with time. At first, they suspected something local, perhaps interference from the equipment, or even something as mundane as debris inside the antenna. There is a well-known detail in this story involving pigeons that had taken up residence in the antenna, leaving behind what was politely described as white dielectric material. The pigeons were removed, the antenna was cleaned, and yet the noise remained. No matter where they pointed the instrument, the signal persisted. Eventually they realized that what they were detecting was not a problem to be eliminated. It was a discovery. At almost the same time, a group of physicists at Princeton University, including Robert Dick and Jim Peebles, had been preparing to search for exactly this kind of radiation. When Penzias and Wilson learned of their work, the pieces fell into place. The background noise they had detected was the cosmic microwave background, the oldest light in the universe, a faint afterglow from a time when the universe first became transparent. The temperature of this radiation today is about 2.7 Kelvin, just a few degrees above absolute zero. It is incredibly uniform with nearly the same intensity in every direction, but not perfectly uniform. And it is in those tiny imperfections that the real story begins to unfold. In the early 1990s, a satellite called the Cosmic Background Explorer, or COBE, was launched by NASA to study this radiation in greater detail. One of the key scientists involved in this mission was George Smoot. COBE was designed to measure both the overall spectrum of the cosmic microwave background and its tiny variations in temperature. The results were remarkable. COBE confirmed that the spectrum of the radiation matched that of a nearly perfect black body, exactly as predicted by the Big Bang model. But more importantly, it detected slight anisotropies, small differences in temperature across the sky, variations of about 1 part in 100,000. These tiny fluctuations represent regions where the density of matter in the early universe was slightly higher or lower than average. They are the earliest detectable seeds of structure. Without them, the universe would remain almost perfectly smooth, and gravity would have nothing to amplify. No galaxies would form, no clusters, no cosmic web, just a vast, uniform expanse. But because of these small variations, structure could begin to grow. Over time, gravity would pull matter towards slightly denser regions, increasing the contrast. Small differences would become larger. Subtle variations would evolve into the complex structures we observe today. Understanding these fluctuations requires looking at how photons behaved in the early universe. One important effect is known as the Sachs-Wolfe effect. These are named after Rainer Sachs and Arthur Wolfe. This effect describes how photons are influenced by gravitational potential wells as they travel through the universe. If a photon climbs out of a region of higher gravitational potential, it loses energy and appears slightly cooler. If it falls into such a region, it gains energy and appears slightly warmer. These shifts contribute to the temperature variations observed in the cosmic microwave background. There are also other processes at play, including acoustic oscillations. Before recombination, the universe behaves somewhat like a fluid, with pressure from photons and gravity from matter interacting to create waves. These waves left characteristic patterns in the distribution of temperature fluctuations. Later missions, such as the Wilkinson Microwave Anisotropy Probe, and often called WMAP, and the Planck satellite operated by the European Space Agency, have mapped these patterns with extraordinary precision. They have provided detailed measurements of the size, distribution, and statistical properties of the fluctuations. From this data, scientists have been able to determine key parameters of the universe: its age, which is approximately 13.8 billion years, its composition, including the proportions of ordinary matter, dark matter, and dark energy, and its overall geometry, which appears to be very close to flat. But as the data has become more precise, new questions have also emerged. There are subtle anomalies in the cosmic microwave background that do not fit perfectly within the simplest models. For example, there are slight asymmetries between different regions of the sky. There are features sometimes referred to as the cold spot, a region that appears slightly cooler than expected. There are alignments in the large-scale patterns that have been informally called the axis of evil, a name chosen with a touch of humour, but reflecting genuine curiosity. These anomalies are not large enough to overturn the standard cosmological model, but they serve as reminders that our understanding is still evolving. They invite further investigation, more precise measurements, and new ideas. What makes the cosmic microwave background so powerful is that it provides a direct link to the early universe. It is not inferred from later structures or indirect observations. It is a relic, a signal that has travelled almost unchanged for billions of years. By studying it, we are effectively looking back to a time when the universe was only a few 100,000 years old, a time when matter and radiation were just beginning to separate, a time when the seeds of all future structure were already present, but only as faint imprints. There is something quietly profound about that. The idea that the entire complexity of the universe, galaxies, stars, planets, and even life, can be traced back to tiny fluctuations in a nearly uniform field. Small differences in temperature measured across the sky, holding within them the blueprint of everything that would come later. And as we continue to study these patterns, refining our measurements and expanding our understanding, we're not just learning about the past, we're learning about the processes that shape the universe into what it is today. From these faint variations, gravity would begin its slow work, drawing matter together, amplifying differences, turning subtle patterns into visible structure. And from that process, over vast stretches of time, the universe would begin to take on a more familiar form. After the universe became transparent, something curious followed. Not a burst of light, not an immediate display of stars, but a long quiet interval. A period where the universe, though filled with matter and radiation, remained almost completely dark. This era is often referred to as the Cosmic Dark Ages. It began shortly after recombination, when neutral atoms first formed and photons were finally free to travel. At this point, the universe was filled mostly with hydrogen and helium gas, spread out in a relatively uniform way, with only slight variations in density inherited from earlier fluctuations. There were no stars yet, no galaxies, no sources of visible light, only a faint afterglow from the cosmic microwave background, gradually cooling as space expanded. If you could somehow observe the universe during this time, you would not see much in the way of structure, just vast, diffuse clouds of gas, slowly evolving under the influence of gravity. But beneath this apparent simplicity, something important was happening. Structure was beginning to form, very slowly, very quietly, and not just through the matter we can see. A significant part of this process was driven by something far more elusive: dark matter. Unlike ordinary matter, which interacts through electromagnetism and can emit or absorb light, dark matter does not interact with light at all, at least not in any way we have detected. It does not glow, it does not reflect. It passes through ordinary matter almost without interaction, and yet its presence is revealed through gravity. Observations of galaxy rotation curves, first carefully studied by Vera Rubin and her colleagues, showed that galaxies rotate in a way that cannot be explained by the visible matter alone. There must be additional mass, distributed in a way that extends beyond the luminous parts of galaxies. This unseen mass is what we call dark matter. In the early universe, dark matter played a crucial role. Because it does not interact with radiation, it was able to begin clumping together earlier than ordinary matter. While normal matter was still tightly coupled to photons, and constantly interacting and being smoothed out, dark matter could start forming gravitational wells. Regions where its density was slightly higher would attract more dark matter, gradually building up structure. These early clumps acted like scaffolding, frameworks around which ordinary matter would later gather. As the universe expanded and cooled, ordinary matter began to fall into these dark matter wells, drawn in by gravity. Over time, this process would lead to the formation of increasingly dense regions, the beginnings of what would eventually become stars and galaxies. But during the Dark Ages, this process was still in its early stages. The density contrasts were small, the structures were faint and diffuse, and without stars there was no visible light to illuminate them. Despite this, the universe was not entirely silent. There is a subtle signal that comes from this era, one that scientists are actively trying to detect and understand. It is based on a specific property of hydrogen, the most abundant element in the universe. Neutral hydrogen atoms can undergo a transition involving the alignment of the spins of the proton and electron. This transition produces radiation with a wavelength of about 21 centimeters. This is known as the 21 centimeter line. By observing this radiation, scientists can probe the distribution and state of hydrogen gas across cosmic time. This approach is called 21 centimeter cosmology. It offers a way to study the universe during periods that are otherwise difficult to observe directly, including the Dark Ages. One experiment that has explored this signal is called EDGES, which stands for Experiment to Detect the Global Epoch of Reionization Signature. In 2018, researchers working with EDGES reported a detection of a signal that may be associated with the early stages of cosmic structure formation. Interestingly, this signal appeared stronger than expected, suggesting that the hydrogen gas was cooler than predicted. This result has sparked considerable discussion and investigation. Some interpretations suggest that it could hint at interactions between dark matter and ordinary matter. Others propose more conventional explanations involving astrophysical processes. At present, the result remains an active area of research, with additional experiments working to confirm and refine these measurements. Regardless of the outcome, and the 21 centimeter line represents a powerful tool, a way to listen, in a sense, to the quiet evolution of the universe during its darkest period. Returning to dark matter itself, while it is widely accepted as a key component of cosmology, its exact nature is still unknown. The most commonly discussed model is cold dark matter, which assumes that dark matter particles move relatively slowly and can clump together efficiently. This model successfully explains many large-scale features of the universe, including the formation of galaxies and the structure of the cosmic web. However, there are also alternative models that explore different possibilities. Warm dark matter, for example, consists of particles with slightly higher velocities. This would lead to smoother structures on small scales, potentially addressing certain discrepancies between simulations and observations. Another possibility is self-interacting dark matter, where dark matter particles can interact with each other through forces other than gravity. This could affect how dark matter is distributed within galaxies, leading to differences in density profiles. These models are still being tested, and each has its own implications for how structure forms over time. What remains consistent across these ideas is the central role of gravity. Even in the absence of light, even in the absence of stars, gravity continues to shape the universe, pulling matter together, amplifying small differences, gradually transforming a nearly uniform distribution into something more structured. As time passes, these processes continue, and regions of slightly higher density grow denser. Gas falls inward, temperatures rise in localized areas, and eventually the conditions become suitable for a new transition. The formation of the first stars. These stars will bring light back into the universe. They will ignite nuclear fusion, produce heavier elements, and begin to alter the surrounding environment in profound ways. But before that happens, there is this long, quiet interval, a time when the universe is still simple, still dark, but already beginning to organize itself. A time when the foundations of all future structure are being laid, not through sudden events, but through the steady, patient influence of gravity acting over immense distances. a slow gathering, a quiet preparation for the moment when the first light returns. As the slow work of gravity continued, something began to change within those quiet, dark regions of the universe. Gas, mostly hydrogen with some helium, was no longer evenly spread. It had started to gather. Very gently at first, drawn into the gravitational wells created by dark matter, forming clouds that grew denser over time. As these clouds contracted, another process began to take hold: heating. When gas falls inward under gravity, it does not simply compress. Its particles begin to move faster, colliding more frequently, increasing the temperature of the region. This is a key idea in astrophysics. Gravitational collapse leads to heating, and if the collapse continues long enough, the temperature at the center of a cloud can rise to extraordinary levels. For the first time since the earliest moments of the universe, where conditions began to resemble those intense environments where nuclear reactions could occur. These collapsing regions gave birth to the first stars. They are known as Population 3 stars. The name may sound slightly out of order, but it reflects the history of their classification rather than their sequence of formation. Population 3 stars are the earliest generation, formed from pristine material that had not yet been enriched by heavier elements. Unlike later stars, which contain a mixture of elements produced by previous generations, these stars were composed almost entirely of hydrogen and helium. This made them very different from stars like our Sun. Without heavier elements, often referred to as metals in astronomy, the cooling processes within these early gas clouds were less efficient. As a result, the collapsing clouds tended to form much more massive stars. Research by astrophysicists such as Volker Bromm and Naoki Yoshida suggests that many of these early stars may have had masses tens or even hundreds of times greater than that of the Sun. Some models indicate masses exceeding 100 solar masses. These were not small, stable stars. They were enormous, short-lived, and intensely luminous. Because of their high mass, the pressure and temperature at their cores rose rapidly. This triggered nuclear fusion. At its most basic level, fusion is the process by which lighter atomic nuclei combine to form heavier ones, releasing energy in the process. In stars, the most common initial reaction involves hydrogen nuclei, which are simply protons combining to form helium. This process releases energy because the resulting helium nucleus has slightly less mass than the sum of its parts. That difference in mass is converted into energy. As described by Einstein's relation, energy is equal to mass multiplied by the speed of light squared. Even a small difference in mass produces a large amount of energy. This energy provides the outward pressure that balances the inward pull of gravity, allowing the star to reach a stable state, at least for a time. For Population 3 stars, this balance was intense and short-lived. Their large masses meant they burned through their nuclear fuel very quickly. Some may have lived for only a few million years, a brief existence compared to stars like the Sun, which can shine for billions of years. Despite their short lives, these first stars had a profound impact on the universe. Inside their cores, nuclear reactions produced heavier elements. Helium could fuse into carbon, carbon into oxygen, and in the most massive stars, fusion could continue to produce elements up to iron. These processes are known collectively as stellar nucleosynthesis. When these stars reached the end of their lives, many of them likely ended in dramatic events. Some exploded as supernovae, dispersing the elements they had created into the surrounding space. Others may have collapsed directly into black holes, depending on their mass. This is where another important pathway emerges: the formation of the first black holes. If a star is massive enough, the inward pull of gravity at the end of its life can overwhelm all opposing forces, leading to collapse. In some cases, this collapse produces a black hole, an object so dense that not even light can escape its gravitational pull. These early black holes may have served as seeds for the supermassive black holes found at the centers of galaxies today. Observations of distant quasars powered by supermassive black holes suggest that such objects already existed when the universe was relatively young. Understanding how they formed so quickly remains an active area of research. Some models propose that direct collapse of massive gas clouds, without forming a star first, could produce intermediate mass black holes. Others suggest that repeated mergers and rapid accretion of matter could build up mass over time. Regardless of the exact pathway, it is clear that the first generation of stars played a key role in shaping these early structures. But perhaps the most important legacy of these stars is chemical. Before their formation, the universe contained almost no elements heavier than helium. After their life cycles, new elements were introduced into the cosmos. Carbon, oxygen, nitrogen, and others were scattered into the surrounding gas. This process is known as chemical enrichment. It changed the composition of the universe in a fundamental way. With the presence of heavier elements, new possibilities emerged. Gas clouds could cool more efficiently. Future generations of stars could form with lower masses and longer lifetimes. Planets, which require elements like silicon and iron, could eventually begin to form. In a sense, these first stars acted as cosmic forges, transforming a simple mixture of hydrogen and helium into a richer and more complex environment. And as they did so, they also began to alter the radiation environment of the universe. These stars were extremely bright, emitting large amounts of ultraviolet radiation. This radiation had enough energy to ionize neutral hydrogen, stripping electrons away from atoms. As more stars formed and more radiation was produced, this process began to affect the surrounding intergalactic medium. The neutral gas that had formed during recombination started to become ionized once again. Not everywhere at once, but in patches, spreading outward from the first luminous sources. This marked the beginning of another major transition, a shift from a neutral universe back to an ionized one, a process that gradually transformed the large-scale properties of the cosmos. And as the number of stars increased, their collective influence grew stronger. Light returned to the universe, not as a uniform glow, but as countless individual sources, each one a point of energy, shaping its surroundings, each one contributing to the gradual lifting of the cosmic darkness. From the quiet collapse of gas clouds to the ignition of nuclear fusion, the universe had taken another step, from darkness to light, from simplicity to increasing complexity. And with that first light, the stage was set for a transformation that would ripple across the entire universe. As the first stars ignited and began to shine, their influence extended far beyond their immediate surroundings. They did not simply illuminate the darkness, they began to change the state of the universe itself. The radiation emitted by these early stars, particularly in the ultraviolet range, carried enough energy to interact with the neutral hydrogen that filled the cosmos. When a high-energy photon encounters a hydrogen atom, it can remove the electron from the proton, breaking the atom apart. This process is known as ionization, and as more stars formed, more of these ionizing photons were produced. Gradually, regions of neutral hydrogen began to transition back into a plasma of free electrons and protons. This marked the beginning of a process known as reionization. The name reflects the fact that hydrogen had previously been ionized in the very early universe, then became neutral during recombination, and was now being ionized once again. But this was not a sudden or uniform transformation. Reionization unfolded in a patchwork. Small regions around the first stars and galaxies became ionized first. These regions expanded outward, forming bubbles of ionized gas within a still neutral background. As more sources of radiation appeared, these bubbles grew larger and began to overlap. Over time, the universe transitioned from mostly neutral to mostly ionized. This process likely took hundreds of millions of years. It was gradual, uneven, and deeply connected to the formation of the first luminous structures. Understanding what powered reionization is an ongoing area of research. One of the primary candidates is the population of early stars themselves. Population 3 stars, along with subsequent generations of stars, emitted large amounts of ultraviolet radiation. Because these stars were often massive and hot, their radiation was particularly effective at ionizing hydrogen, but stars are not the only possible contributors. Another important source may be quasars. Quasars are extremely luminous objects powered by accretion onto supermassive black holes. As matter falls into a black hole, it forms a rapidly spinning disk known as an accretion disk. Friction and gravitational energy heat this disk to very high temperatures, producing intense radiation across a wide range of wavelengths. This radiation can also ionize hydrogen. The question of how much quasars contributed to reionization compared to stars is still being studied. Astrophysicist Abraham Loeb and others have explored these competing scenarios, using both theoretical models and observational data to estimate the relative importance of different sources, and current evidence suggests that early stars were likely the dominant contributors, especially in the earlier stages of reionization, while quasars may have played a more significant role later on. But the balance is not yet fully settled. What is clear is that reionization was not a simple process with a single cause. It was the result of many sources, many regions, and many interactions, all unfolding across vast distances. As these ionized bubbles expanded and merged, they began to change the behavior of matter in the universe. Ionized gas interacts differently with radiation than neutral gas. It can absorb and scatter light in new ways. It can also influence how gas cools and collapses. This had important consequences for the formation of galaxies. In regions that became ionized, the increased energy of the gas could inhibit the collapse of smaller structures. Gas that is too hot resists gravitational compression. This means that reionization may have suppressed the formation of smaller galaxies in certain regions, while allowing larger structures to continue growing. In this way, reionization did not just illuminate the universe, it shaped the distribution of matter. It influenced which regions could form stars and which could not. It introduced a feedback process, where the formation of stars affected the environment, which in turn influenced the formation of future stars. This interplay between radiation and matter added a new layer of complexity to the evolution of the universe. Before reionization, the behavior of matter was dominated by gravity and basic cooling processes. After reionization, radiation became an active participant, altering conditions across large scales. This marks an important shift. The universe was no longer just evolving under simple physical laws in a mostly uniform environment. It was becoming structured, dynamic, Interconnected. Regions of space began to differ more significantly from one another. Some became rich in galaxies and star formation. Others remained more diffuse. The cosmic landscape was taking on a more intricate form. Observationally, studying rionization is challenging because it occurred so early, and because it involves diffuse gas rather than bright objects. It is not directly visible in the same way as stars or galaxies. However, astronomers can infer its progress by studying the light from distant quasars and galaxies. As light travels through space, it interacts with intervening hydrogen. Neutral hydrogen absorbs specific wavelengths of light, particularly in the ultraviolet. By examining how much of this light is absorbed, scientists can estimate how much neutral hydrogen was present at different times. These observations suggest that reionization was largely complete by around 1 billion years after the beginning of the universe's expansion, though the exact timeline is still being refined. There are also ongoing efforts to detect signals from this era using radio telescopes, particularly through observations of the 21-centimeter line of hydrogen. These measurements aim to map the distribution of neutral and ionized regions over time, providing a more detailed picture of how reionization unfolded. As this transition progressed, the universe became increasingly transparent to ultraviolet light. The fog of neutral hydrogen that had once filled space was gradually lifted. Light from distant objects could travel more freely, and the structures that had been forming quietly in the background began to reveal themselves more clearly. What had started as small fluctuations in density had grown into larger and more complex systems. Clusters of matter, early galaxies, regions where stars were forming in significant numbers. The universe was no longer in its quiet, dark phase. It had entered a period of increasing activity and complexity. From the first stars to the reionization of the intergalactic medium, each step built upon the last, each process shaping the conditions for the next. And as these structures continued to grow and evolve, they began to organize into something even larger. Galaxies, bound together by gravity, containing billions of stars, each contributing to the ongoing story of the universe. A story that continues to unfold, shaped by forces that began their work in these earliest, transformative moments. As structure continued to grow, the universe began assembling matter into increasingly organized systems, not just isolated stars or scattered clouds of gas, but vast, gravitationally bound collections of billions of stars. Galaxies. These structures did not appear fully formed. They emerged gradually, shaped by the interplay between gravity, gas dynamics, radiation, and the unseen influence of dark matter. At the heart of most models of galaxy formation lies the idea of dark matter halos. These halos are large, roughly spherical regions where dark matter has collapsed under its own gravity, forming dense concentrations. Because dark matter interacts primarily through gravity and not through electromagnetic forces, it began clumping earlier than ordinary matter. As a result, these halos acted as the first stable structures in the universe. Within these halos, ordinary matter, mostly hydrogen and helium gas, began to fall inward. As the gas collapsed, it heated up, cooled through radiation, and eventually fragmented into smaller regions where stars could form. Over time, these processes led to the emergence of galaxies embedded within dark matter halos. The size and shape of a galaxy are influenced by many factors: the mass of the halo, the rate at which gas falls in, the efficiency of cooling, and the history of mergers with other systems. Some galaxies grow through gradual accumulation. Others form through collisions and mergers, where smaller galaxies combine to create larger ones. These interactions can trigger bursts of star formation, reshaping the structure of the galaxy. But as astronomers began to study galaxies in more detail, they noticed something unexpected. The way galaxies rotate did not match what would be predicted based on the visible matter alone. In a simple gravitational system where most of the mass is concentrated toward the center, objects farther from the center should move more slowly. This is similar to how planets in the solar system behave. Mercury moves faster than Earth, and Earth moves faster than Mars because the gravitational influence of the Sun decreases with distance. Yeah, so if galaxies were composed only of visible matter, stars at the outer edges should orbit more slowly than those near the center. But that is not what observations show. In the 1970s, Vera Rubin and her collaborator Kent Ford carefully measured the rotation curves of spiral galaxies. They found that stars far from the center were moving at roughly the same speed as those closer in. The rotation curves were flat. This implied that there was much more mass present than could be accounted for by visible stars and gas. And importantly, this mass was distributed over a large region, extending well beyond the luminous parts of the galaxy. This provided strong evidence for the existence of dark matter halos. Without this additional mass, the observed rotation speeds would not be possible. The outer regions of galaxies would simply not have enough gravitational pull to keep stars moving at those speeds. So dark matter became a central part of the explanation. It provides the gravitational framework within which galaxies form and evolve. It explains not only rotation curves but also the dynamics of galaxy clusters, gravitational lensing observations, and the large-scale structure of the universe. However, not everyone has been entirely satisfied with this interpretation. In the early 1980s, a physicist named Mordechai Milgram proposed an alternative idea known as modified Newtonian dynamics, or MOND. Instead of introducing unseen matter, MOND suggests that the laws of gravity themselves might behave differently at very low accelerations. In this framework, when the gravitational acceleration falls below a certain threshold, the relationship between force and motion changes. This modification can produce flat rotation curves without requiring dark matter. MOND has had some success in explaining certain features of galaxy rotation. In particular, it can reproduce the observed relationship between the distribution of visible matter and the rotation speed. But it faces challenges in other areas. For example, it does not easily account for observations of galaxy clusters or the detailed structure of the cosmic microwave background. There have been attempts to extend MOND into a more complete relativistic theory, such as TeVeS, developed by Jacob Bekenstein, but these models are still being tested. At present, the dark matter framework remains the most widely accepted explanation, but the existence of alternatives like MOND serves as a reminder that our understanding of gravity and matter is still evolving. It encourages careful examination of assumptions and continued exploration of new ideas. Returning to galaxy formation, once stars begin to form within a galaxy, they do not simply remain passive components. They actively influence their surroundings. This is where feedback processes become important. When massive stars reach the end of their lives, they often explode as supernovae. These explosions release enormous amounts of energy, heating the surrounding gas and driving it outward. This can regulate star formation by preventing gas from collapsing too quickly. In some cases, it can even expel gas from the galaxy entirely. Similarly, Supermassive black holes at the centers of galaxies can produce powerful outflows. As matter falls into the black hole, it releases energy that can heat and push away gas. This is known as active galactic nucleus feedback. These processes act as a kind of balancing mechanism. Too much star formation can lead to strong feedback, which then suppresses further star formation. Too little, and gas can continue to accumulate and collapse. The result is a dynamic system, constantly adjusting and evolving. Galaxies are not static objects. They change over time. They grow through mergers. They form new stars. They lose gas. They interact with their environment. Even their shapes can evolve. Spiral galaxies, with their rotating disks and well-defined arms, can transform into elliptical galaxies through collisions and mergers. Elliptical galaxies, in turn, may have formed from the remnants of earlier systems. Over billions of years, these processes create a rich diversity of galaxy types. Some are small and irregular, others are vast, containing hundreds of billions of stars. Each one carries a history, shaped by both internal processes and external interactions. And yet, beneath this complexity, there is a common thread: gravity. From the earliest fluctuations in the cosmic microwave background, to the formation of dark matter halos, to the assembly of galaxies, gravity has been the guiding force, pulling matter together, amplifying small differences, building structure across vast scales. At the same time, other processes such as radiation, gas dynamics and feedback add layers of complexity. So they shape how matter behaves within these gravitational frameworks. They determine how efficiently stars form, how galaxies evolve, and how energy is distributed. The result is a universe that is both structured and dynamic, ordered yet constantly changing. And as galaxies continue to form and evolve, they do not exist in isolation. They are part of larger patterns, clusters of galaxies, filaments stretching across space, vast regions of emptiness between them, all connected in a larger network, a structure that extends far beyond any single galaxy, a structure that reflects the history of the universe itself from its earliest moments to its present form. As galaxies continued to form and evolve, a larger pattern began to reveal itself, not immediately, and not in a way that is obvious when looking at a single region of space, but gradually as observations expanded and simulations improved, a deeper structure became clear. Galaxies are not scattered randomly. They are arranged in a vast interconnected network, a structure that stretches across the observable universe, linking clusters of galaxies through long, delicate filaments, while leaving enormous regions of near emptiness in between. This is known as the cosmic web. To understand how such a structure forms, it helps to return to the earliest fluctuations in density. Those tiny variations, imprinted in the cosmic microwave background, provided the initial conditions. Regions that were slightly denser began to attract more matter through gravity. Over time, these regions grew, but not in a uniform or spherical way. Gravity does not pull equally in all directions when the distribution of matter is uneven. Instead, matter tends to collapse first along one dimension, forming sheets, then along another, forming filaments. And finally, at the intersections of these filaments, matter accumulates into dense nodes. This process was described by the Soviet physicist Yakov Zeldovich through what is now known as the Zeldovich approximation. It provides a way to model how initial density fluctuations evolve under gravity, leading to the formation of large-scale structure. In this picture, the universe begins as a nearly uniform field with slight variations. As time passes, matter flows along paths determined by gravitational gradients, first forming planar structures, sometimes referred to as pancakes, then breaking into filaments, and eventually concentrating into clusters. The result is a web-like pattern, filaments stretching across tens to hundreds of millions of light years, clusters of galaxies at the intersections, where multiple filaments meet, and vast voids in between, where relatively little matter is present. These voids can span tens of millions of light years, containing only a small fraction of the average cosmic density. They are not completely empty, but they are among the least dense regions in the universe. If you could step back and view the universe on its larger scales, you would not see a uniform distribution of galaxies. You would see something more like a sponge or a network. Bright nodes connected by thin strands with large dark regions in between. This structure has been confirmed through large observational surveys, such as the Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies. These maps reveal the cosmic web in striking detail, but observation is only one part of the story. To understand how this structure forms and evolves, scientists rely on numerical simulations. These simulations model the behavior of dark matter, gas, and radiation over cosmic time, starting from initial conditions based on observations of the early universe. Two well-known examples are the Illustri simulation and the Eagle simulation. These projects use powerful supercomputers to track the evolution of billions of particles, representing both dark matter and ordinary matter. They incorporate physical processes such as gravity, gas cooling, star formation, and feedback from supernovae and black holes. What emerges from these simulations is remarkably consistent with what we observe. A cosmic web of filaments, clusters, and voids, galaxies forming within dark matter halos, structures growing through mergers and accretion. These simulations do not simply recreate the universe as it is. They help us understand why it looks the way it does. They allow scientists to test different models, adjust parameters, and see how changes affect the outcome. In this way, they serve as a bridge between theory and observation. Another important concept in understanding the cosmic web is bias. This does not refer to preference in the usual sense, but to the relationship between the distribution of galaxies and the underlying distribution of matter. Galaxies do not trace the distribution of matter perfectly. They tend to form in regions where the density of matter is higher. This means that the visible structure of the galaxies we observe is a biased tracer of the total matter distribution. Dark matter, which makes up most of the mass, is more smoothly distributed, forming the underlying framework. Galaxies highlight the densest regions within that framework. Understanding this bias is important for interpreting observations. It allows scientists to infer the distribution of dark matter from the distribution of galaxies, even though dark matter itself cannot be observed directly. It also helps in measuring cosmological parameters such as the overall matter density and the amplitude of fluctuations. What emerges from all of this is a picture of the universe as a connected system, not a collection of isolated objects, but a network. Each galaxy is part of a larger structure. Each cluster is connected to others through filaments. Matter flows along these filaments, feeding the growth of galaxies and clusters over time. Even voids, the vast empty regions, play a role. They expand faster than denser regions, influencing the dynamics of the surrounding structure. There is a kind of balance to it. Dense regions grow denser, empty regions become emptier. and the overall pattern becomes more pronounced as time goes on. There is something quietly elegant about this. From tiny fluctuations in the early universe, a vast and intricate structure has emerged, not through a central plan or design, but through the consistent application of physical laws over immense spans of time, gravity pulling matter together, expansion stretching space apart, thus small differences growing into large-scale patterns, and all of it interconnected. If you were to follow a single particle of matter through this process, it would not remain in isolation. It would move along gravitational pathways, influenced by the distribution of matter around it. It might become part of a filament, or fall into a cluster, or drift into a void. Its path would be shaped by the collective behavior of everything else. In that sense, the cosmic web is not just a structure, it is a dynamic system, a network through which matter and energy flow, a record of the universe's history, written in the arrangement of galaxies and the distribution of matter. And as we continue to map this structure in greater detail using both observations and simulations, we gain a deeper understanding of how the universe evolved. From the earliest fluctuations to the vast patterns we see today, a progression from simplicity to complexity, from near uniformity to a richly structured cosmos, and within that structure, galaxies continue to form, evolve, and interact, each one a part of the larger network, each one shaped by the same underlying forces that have been at work since the beginning, a quiet, continuous unfolding, connecting the smallest scales to the largest and revealing the shape of everything. When we look out into the night sky, even with the most powerful telescopes, we're not seeing the universe as it is now. We're seeing it as it was. This is not a limitation of our instruments, but a consequence of how light travels. Light moves at a finite speed, approximately 300,000 kilometers per second. That may sound incredibly fast, and on human scales it certainly is, but across cosmic distances even light takes time. When we observe the sun, we're seeing it as it was about 8 minutes ago. When we look at the nearest star system beyond our own, Alpha Centauri, we see it as it was over 4 years ago. And when we observe distant galaxies, millions or billions of light years away, we are looking deep into the past. This concept is known as look-back time. The farther away an object is, the longer its light has been travelling to reach us, and the further back in time we are observing it. In this way, astronomy becomes a kind of time machine, not one that allows us to travel backward, but one that allows us to observe earlier stages of the universe's history. By studying objects at different distances, we can piece together a timeline. Nearby galaxies show us what the universe looks like in its more recent state. Distant galaxies reveal earlier phases when structures were still forming, and the cosmic microwave background takes us back even further, to a time when the universe was only a few 100,000 years old. But there are limits to how far we can see. One of these limits is known as the cosmic horizon. Because the universe has a finite age, and because light travels at a finite speed, there is a maximum distance from which light has had time to reach us since the beginning of cosmic expansion. This defines the observable universe. Beyond this horizon, there may be more universe, perhaps much more, but we cannot observe it directly because its light has not yet arrived. There is also another kind of horizon, related to the expansion of the universe itself. As space expands, distant regions can recede from us faster than the speed of light, not because they are moving through space in the usual sense, but because the space between us is stretching. In such cases, light emitted from those regions may never reach us, even given infinite time. This creates a boundary to what we can ever observe, a limit not just in space, but in possibility. Within these boundaries, we gather information through light and other forms of radiation. But interpreting that information is not always straightforward. Light does not always travel in a straight line. It can be influenced by gravity. According to Einstein's theory of general relativity, mass and energy curve space-time and light follows those curves. Then this leads to a phenomenon known as gravitational lensing. First discussed in detail by Fritz Zwicky in the 1930s, gravitational lensing occurs when a massive object, such as a galaxy or a cluster of galaxies, bends the path of light from a more distant source. This can magnify the background object, distort its shape, or even produce multiple images. In some cases, it creates rings or arcs of light, known as Einstein rings. Gravitational lensing has become a powerful tool in astronomy. It allows scientists to observe objects that would otherwise be too faint or too distant. It also provides a way to map the distribution of mass, including dark matter, by analyzing how light is bent. In this sense, gravity itself becomes a kind of natural telescope, enhancing our ability to see deeper into the universe. But even with these tools, there are challenges. One of the most intriguing in recent years is known as the Hubble tension. This refers to a discrepancy between different measurements of the rate at which the universe is expanding. The expansion rate is quantified by the Hubble constant. One method of measuring this constant involves observing relatively nearby objects, such as Cepheid variable stars and Type I supernovae, and building a distance ladder. This approach has been refined by researchers such as Adam Rees and his collaborators. Another method involves analyzing the cosmic microwave background, particularly data from the Planck satellite, and using it to infer the expansion rate based on a model of the early universe. These two methods, which rely on very different types of observations, produce slightly different values. The difference is not enormous, but it is statistically significant, and importantly, it persists even as measurements become more precise. This raises the possibility that our current models may be missing something. Perhaps there are additional physical processes at work. Perhaps our understanding of dark energy or the behavior of matter in the early universe needs to be refined. Or perhaps there are subtle systematic effects in the measurements themselves. At present there is no consensus, but the tension serves as a reminder that even well-established frameworks can contain uncertainties, and that new discoveries often arise from such discrepancies. All of this highlights a broader point. Astronomy is not direct observation in the way we experience objects around us. We do not touch distant galaxies. We do not interact with them in real time. Instead, we receive signals, light, radio waves, X-rays, gravitational waves, each carrying information, but also shaped by the processes they have encountered along the way. We interpret these signals using models, theories, and careful analysis. We reconstruct the history of the universe from patterns in data, from spectra, from brightness, from motion. It is a process that combines observation with inference, measurement with interpretation, and while it has led to remarkable insights, it also requires humility. Because what we see is always filtered by distance, filtered by time, filtered by the limitations of our instruments and our understanding. Yet despite these limits, the picture that emerges is both detailed and coherent. Though we can trace the evolution of the universe from its early, nearly uniform state to the complex structures we observe today. We can measure its age, its composition, and its expansion. We can map its large-scale structure and study the behavior of matter under extreme conditions, all from signals that have travelled across vast stretches of space and time. There is something quietly remarkable about that. The idea that by observing faint patterns of light, we can reconstruct events that took place billions of years ago. That we can look across the universe and see not just distant objects, but earlier chapters of a story that continues to unfold. And as our instruments become more sensitive, as our models become more refined, and as new observations are made, that story becomes clearer. Not complete, not final, but increasingly detailed. A narrative assembled piece by piece, guided by evidence, shaped by interpretation, and always open to revision as new information comes to light. As we follow the story of the universe forward in time, something unexpected begins to emerge. For a long while, gravity was the dominant influence on large scales. It pulled matter together, shaped galaxies, and built the cosmic web. It seemed reasonable to expect that, over time, gravity might slow the expansion of the universe. After all, if everything is pulling on everything else, the expansion should gradually decelerate. That was the expectation for many years. But in the late 1990s, observations revealed something quite different. Two independent research teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, studied distant Type 1a supernova. These stellar explosions serve as standard candles, meaning their intrinsic brightness is known. By comparing how bright they appear to us, astronomers can determine their distance. And by measuring their redshift, they can determine how fast they're moving away. When these teams analysed the data, they found that distant supernovae were dimmer than expected. This suggested that they were farther away than predicted by a universe that was slowing down. In other words, the expansion of the universe was not decelerating. It was accelerating. This was a surprising result. It implied that something was counteracting gravity on large scales, something that was pushing space apart. This mysterious influence is known as dark energy. Dark energy is not directly observed in the way that stars or galaxies are. It is inferred from its effects on the expansion of the universe. In the current cosmological model, dark energy makes up about 70% of the total energy content of the universe. Ordinary matter accounts for only about 5%. Dark matter contributes about 25%. So most of the universe is composed of something that we do not yet fully understand. One of the simplest ways to describe dark energy is through the cosmological constant, a term originally introduced by Albert Einstein. In this interpretation, dark energy is a property of empty space itself, a constant energy density that remains the same as space expands. As the universe grows, more space is created, and with it, more of this energy. This leads to a repulsive effect on large scales driving the acceleration. However, this raises a significant question. In quantum field theory, even empty space is not truly empty. It contains fluctuations, virtual particles that appear and disappear. These fluctuations contribute to what is known as vacuum energy. When physicists attempt to calculate the expected energy density of the vacuum, the result is enormous, far larger than what is observed. The discrepancy between the theoretical prediction and the observed value is one of the largest known mismatches in physics. It is sometimes described as being off by a factor of 10 raised to the power of 120. This is known as the vacuum energy problem. It suggests that our understanding of the relationship between quantum mechanics and gravity is incomplete. Because of this, some physicists have explored alternative ideas. One such idea is quintessence, a concept introduced by Michael Turner. In this model, dark energy is not a constant but a dynamic field that evolves over time. Its energy density can change, and its effects on the expansion of the universe may vary. This opens up the possibility that the acceleration we observe today is part of a larger evolving process. Quintessence models are still being tested, and current observations are consistent with a cosmological constant, but the possibility of a dynamic form of dark energy remains an active area of research. As we move further into these questions, we encounter the limits of our current theories. General relativity describes gravity on large scales. Quantum mechanics describes the behavior of particles on small scales. But combining these two frameworks into a single, consistent theory has proven to be extremely challenging. This is where approaches such as loop quantum cosmology and string cosmology come into play. Loop quantum cosmology, developed in part by Abhay Ashtekar and others, applies ideas from loop quantum gravity to the early universe. In this framework, space-time itself is quantized, composed of discrete units rather than being continuous. One of the interesting outcomes of this approach is the possibility of a cosmic bounce. Instead of a singular beginning where density becomes infinite, the universe may have undergone a previous phase of contraction, followed by a transition into expansion. This avoids the need for a singularity and suggests that the Big Bang may be part of a larger cycle. String cosmology, associated with researchers such as Leonard Susskind, takes a different approach. It builds on string theory, where the fundamental constituents of reality are tiny vibrating strings. In this framework, there may be a vast landscape of possible vacuum states, each corresponding to different physical properties. This leads naturally to the idea of a multiverse, where different regions of space realize different configurations. Our observable universe would be one region within this larger landscape. These ideas are still highly theoretical. They're difficult to test directly, and much of the work remains mathematical. But they offer possible ways to extend our understanding beyond the limits of current models. There are also cosmological models that explore cyclic behavior on large scales. Paul Steinhardt and Neil Turok have developed models in which the universe undergoes repeated cycles of expansion and contraction. In these scenarios, the Big Bang is not a unique beginning, but a transition between phases. Roger Penrose has proposed a related idea known as conformal cyclic cosmology. In this model, the very distant future of one universe, when all matter has decayed and only radiation remains, can be mathematically mapped onto the beginning of a new universe. Time, in a sense, loops through these transitions, though not in a simple or repeating way. These ideas are imaginative, but they are grounded in attempts to address real questions, what happened at the earliest moments we can describe. Whether the universe had a true beginning, and whether the laws of physics we observe today are part of a larger framework. At this stage, it becomes clear that the story of the universe is not complete. We have a detailed understanding of many phases. We can trace the evolution of structure, we can measure the expansion, and map the distribution of matter. But when we approach the deepest questions, the origin of the universe, the nature of dark energy, the unification of physical laws, we reach the edge of what is currently known. And that edge is not a sharp boundary. It is a region of active exploration, a place where ideas are tested, refined, and sometimes replaced, where observation and theory continue to interact, and where new discoveries may reshape the picture once again. And there is something quietly fitting about this. The universe began, as far as we can tell, in a state of simplicity, and over time it has become more complex. Our understanding follows a similar path, from simple models to more detailed ones, from clear answers to deeper questions. And as we look out into the cosmos and back toward its earliest moments, we're not just observing a distant past. We're participating in an ongoing process of discovery, a gradual unfolding of knowledge, shaped by curiosity, evidence, and the willingness to explore what lies just beyond the limits of our current understanding.